SIwave is a power integrity and signal integrity tool. Signal Integrity Wizard, which is this solver, is the main tool for signal integrity analysis. Signal Integrity Wizard is used to study the signal integrity of RF, clock, and control traces. Using this tool, the user can check if the bandwidth is sufficient and if the group delay deficiency is tolerable in any trace. This tool allows users to do transient analysis, eye analysis, and bit error calculations, as well as S-parameter calculations. Users can add IBIS and IBIS-AMI models to the TX and RX side. SIwave supports NRZ as well as PAM4 signals. Let's start. SIwave should not be used to build PCBs. While this is possible, it's not the best way to use SIwave. SIwave can import all kinds of files, different formats. Users of Allegro and Altium can install Ansys ADB translator to produce ADB files, the one that you see here. For users using ORCAD, it is recommended that they use IPC 2581. People using Mentor Expedition should use ODB++ files, this one. For Cadence users, please generate BRD files, board files, and import them to SIwave. To do that, Cadence must be installed on the same computer. Extracta from Cadence must also be installed, and its location should be in the path environment variable. SIwave extracts lots of information from the CAD file. For example, the stack-up, as you can see here, the materials, the components, and the nets. So practically the model is ready to be solved. Before launching the Signal Integrity Wizard, make sure that the SIwave recognizes the differential traces. Selects the differential tab, this one. Usually is going to be empty. Yet the user knows, for example, that he has differential lines in the model. Then what you do is you click Auto Identify. SIwave opens a new dialog box and shows what notations it uses to recognize differential lines, _P, _N. You can change them. If it is correct, if this is what's being used in the CAD tool, then simply click Auto Identify and automatically SIwave will populate the table. Press OK, and bingo. Now we have the differential tab filled with differential lines. The user can also manually select two nets, provided that they are _P, _N. Move the mouse to the display area, right-click, and then select Create Differential Pairs. For example, if I select this pair, let me hide everything, show only traces, you can see them. Let's remove this from the list. Now these two are not listed as differential lines, but they are selected. Right-click here, and you can see Create Differential Pair, and a differential pair will be created. So you give it a name. In this case, you have to specify the name. We go Auto Identify again, use Auto Identify, and the line is back to here. So there are two ways to build differential lines. If you have traces which are made of so many sections simply because there are DC blocks in between, or resistors or inductors, and you want to unite them together as one net, there's a way to do that in SIwave is by creating what we call extended net. And this is the tab of extended net. If you click Auto Identify, as you can see, SIwave uses the letter R to recognize the nets that can be combined together as an extended net. What this means is that SIwave is looking for two traces. They have exactly the same name, but one of them has R at the end. So if you click Auto Identify, it looks around and it can't find anything. So let's create a one. So for example, if I take this one and that's the name of the net. Now we look at this trace is 2v5, so we look at for this 2v5, and we say edit name, and we change the name, and we add R at the end. So now it has a new name. If we go back to extended, and we say auto identify, click OK, and bingo, here we go. It was able to recognize the two. Like we did with the differential, we can also select two nets, and we can then unite them from the screen. So if I select this net, you have to select them from here. And I select this one, so I have selected the two nets. Right click, and now you can do create extended net. And the third way is to come here and simply you enter a new name, for example, test one. And then you click edit, then you have all the nets that you have in the board. Then you can select as many as you want, random, and you can add them, then you click OK. And that's how you can, that's the third way to create extended nets in SIwave. So we go back, we don't have any extended nets. Let's remove this one because we don't have any extended nets. We don't want to build extended nets. We have differential lines, and we also have single ones. Now that our signals have been identified as single or differential or extended, now we can move ahead and go to our solver. And we're going to select the signal integrity wizard. And again, we have single-ended and differential, extended if there are extended, and extended differential. Practically, extended differential are extracted after building the extended. So when you build extended traces, make sure to give them underscore P underscore N at the end of their names, so SIwave can distinguish them as differential, identify them as the differential. In our case, we're going to rely on single ones just to demonstrate how to do signal integrity. I will select from 0 to 7 as the signals, as the traces I want to process. You can select differential if you want. And as I said, extended. But for now, we'll focus on single one just to demonstrate how to set up a problem in signal integrity wizard. So we'll go next, and this is where the fun starts. Before you start doing this, you need to understand what exactly SIwave or signal integrity wizard solver will do for you. It is going to create the following schematic. Let me show it to you. It's going to create a schematic like this in the electronic desktop. Inside SIwave, the solver only calculates the S parameters, which is this box. Yet it will use all the information that you will provide to construct the schematic and set up all these I sources. These are I sources. And these are I probes. And if there are IBIS models, there will be IBIS icons here instead of the I source. So this is important to understand, because then now you know exactly what you need to fill in and which information will be used by SIwave itself and which part is going to be transferred to the electronic desktop circuit. So let's look at first at this dialog box and try to understand the meaning of each column. So in the first column, we have the individual nets. Even if you have differential, it will still put the single ones. And for each one, for each trace, there are two entries. So you see we have one entry here for 0, DQ0, and another one here. This one is connected to a component called mu1, and this one is connected to another component called mu15. Column 2 is the pin name on that component. Expose means I want signal integrity wizard to have a port on that pin. So for example, if you have decoupling capacitors, you're going to have also some pins, but you're not going to expose them. So when you don't expose them, you are asking Signal Integrity Wizard not to have ports on them. Now in column 4, it gives you the name of the component, while column 5 will give you what we call the reference designator of the component, because the same component, you could have so many of them on your PCB. And for each one of them, there's one letter, one name given to each one of them. Column 6 is where you specify whether this is a driver or a receiver. Practically, as we saw in the schematic, you have to put an I source and an I probe. So wherever you put a driver is going to be an I source. So I'm going to select all these lines. Notice when I select all of them, this area get activated. I can specify that this is a driver, and I will say update. And here we go. And here it's a receiver. Update, the same thing. My table is ready. Column 7 is what we call typical. It's being used when you select IBIS models. If you decide to add IBIS models, this is an IBIS component, is where the name of the IBIS file, and this is model selector if you need it, and this is the IBIS model. Usually there are so many models in the same file. The corner simply specify whether you want to use the typical, the minimum, the maximum, the fast, slow. Usually these are different options that exist inside the IBIS model. So if they exist, then you need to select one of them. The last column that you see here, the last column is package RLC. It's related to the IBIS model. If you click it, then whatever information about the package RLC that exists inside the IBIS model will also be used by Signal Integrity Wizard. The most important column now is the excitation. Once you specify driver, you have to tell the system what kind of signal you're going to inject into this driver. And you have so many possibilities. It could be a default pulse, a PRBS, custom bit sequence, or a default clock. And to be able to control these signals, we have here, you go down here in Manage Sources. So in this dialog box is where you define your signals. So for example, for default PRBS, you have to specify the voltage. The type, of course, it's a PRBS. A bit list, if it's a default custom bit sequence, you have to specify the bit sequence. The seed is mainly used when you are defining so many bits in a byte. So 0, 1, from 0 to 7 if you need it. And here is the period. That's for the pulse mainly. It's not necessary for the other signals. It's mainly for the pulse. It's 10 nanosecond. Duty cycle, again, this is mainly for the pulse when you need to specify how much time is given to the 1 and how much time is given to the 0. Then we have the bit rate. So the bit rate is how many bits per second. So in this case, for example, we selected 800 megabits per second. The delay, if you wanted to have a delay in sending the signal, and this is the rise time, and this is the fall time, and this is the internal impedance of the driver. Notice here the note for automatic random bit sequence generation for PRBS source, enter random in the seed field. If you enter random, it will be a random kind of bits. It's not gonna be following the PRBS kind of signals. You can add a new source. So I can add a new source. I can specify, it has to be one of these 4. So I can have another PRBS signal with a different voltage, with a different rising time and falling time. Then if I have something like this and I go back to my table, I will have that selection in the list as source 1. And you can have different kind of signals injected in each one of these traces. So you are not limited by or forced to use the same kind of source for all these drivers. If we are satisfied with the entries that we have here, we proceed to the next dialog box. And this is where we determine the impedance of the receiver. So receiver termination. Let's talk more about the different columns. Again, we have the different lines from DQ0 to DQ7. We have the pin name and we have the part number. That's the part number where is the receiver. This is the receiver. So and this is the designated name for that part. As we said, this part could be used. You could have so many of them on your PCB, and for each one of them there is one reference designator for that component that's connected to this trace. What's VTT and RVT? This is for old stuff like this, DDRs, where you can have a pull-up. This is like a pull-up resistor you add to the trace. And if you do that and you go and you create the schematic, Signal Integrity Wizard will create this pull-up resistor and will add the voltage to it. That's the purpose of these two columns. Of course, here, like you have a termination for the resistor, you could also have a parallel capacitor for the termination on the receiver. If we are satisfied, we go next. So this one is simply the power planes that are connected to the components being used in this analysis. So we know that we are connected to mu1 and mu15. So this is specifying the VDD and the ground. SIwave take that into consideration when it's doing the calculations. Next, the last stage is the stage where we define our solver. So we're going to go through them line by line. So if I go Ansys Electronic Desktop Project Name, that's where you enter the name of the project or the name of the solution. You could have so many solutions with different setups. So for each one of them, you give it a name. Generate netlist instead of schematic. You have the choice. You could say that you don't want to see a schematic. Just create a netlist. But if you select not to go with that, then automatically Signal Integrity Wizard will create the schematic we were talking about. Include user-defined ports. It means if you have additional ports that were not generated by Signal Integrity Wizard, yet you want them to be included as probes, for example, sensors, or maybe power planes ports, this is the right place to where you can add them. The stop time, so this is the definition of the transient solver. Remember, we're going to be doing a transient solution. And so you need to specify the step size, the stop time. And usually we specify it to be like the step size to be 1/5 or 1/10 the rising time, the smallest rising time used with the signals. And if you, and these choices is what exactly you want SIwave to do when it creates the schematic. Do you want it to start running the transient solver immediately, plot the results of the driver, plot the results of the receiver, plot the power rail waveforms? Do you want it to include a quick eye simulation? Do you want it to run it? Do you want it to plot also? So you can tell Signal Integrity Wizard what to do when after creating the schematic in the electronic desktop. The last section, S parameters. This is the only section. Whatever you enter here is what SIwave is going to be using, because this section is related to the S parameter solver. And this is what SIwave is going to be doing only, is running the S parameter solver, then pass the information to the circuit tool to do the rest. So everything we entered before, get copied to the circuit only. SIwave will not use it. So we specify the signal net to be 50 ohm, the power net to be 1 ohm. Remember, we were talking about the power planes and that SIwave consider the power planes connected to your signal. If you click edit here, that's where you do the setup of your S parameter. You specify the range. You specify whether you want to do discrete or interpolating a sweep with accuracy of your desire. This is if you wanted to enforce causality or enforce passivity. This 3D solver, if you included regions and you want HFSS to be used in these regions or Q3D to be used in these regions, then you can select that. Notice here the rising time. This rising time number is connected to the highest frequency in your setup. So if you change this number, if I, for example, I say instead of 3.5, I say 4.0, immediately the number will change here. You will notice that the number changed to 12.5. In our case, the rising time was 35 picosecond, and consequently, we need to simulate our system minimum to 14.28. You can go beyond that if you want. You can change this one. You can say, for example, I want it to go to 20 gig. If you go to 20 gig, the system will say, okay, then I can tolerate a rising time of 2.5. So you can see these two are connected with each other. You can also press on other solver options, and here you can specify the accuracy of your solver. If you select to have custom, then you can have access to the advanced, where you can enter so many other restrictions and limitations and requirements on the mesh, on the distributions. So we're going to leave everything as is, but at least you are aware that you have other options related to temperature and multiprocessing and net processing. This one is where if you wanted to include power planes in your calculations, you can do that. So we'll keep everything as is. We're not going to change anything. We're happy with the setup. Now we are ready to solve. So if press OK, it will start solving. Press OK. Press OK. And it's going to start solving. The first result is from the transient solver. So you see here, the driver. The transient solver plots what the user asks for, the voltage at the driver and the voltage at the receiver. As you can see, we have 111, for example, 00000011. These are PRBS signals. Now notice that the voltage here is half what we asked for. We asked for 1.2. The reason why is because the signal acts as a power divider. So it divides the voltage into half. So whatever voltage you need to see in the output, you need to double it in the setup. So if I want to see 1.2 volt, then I have to put 2.4 volt. If the user doesn't have the license to see an eye, because this is the eye analysis, this is the eye results. If the user doesn't have the license to see an eye diagram or do eye analysis, you can use the transient solver to produce eye diagrams. And the way to do that is simply you go here, an eye diagram, rectangular plot. Make sure to select transient, select any one of these, and you specify here just the unit interval. In our case, we used 800 megabits per second. That's around 1.25 E9 second. E minus 9, sorry, E minus 9. So if I select this and I go ahead, new report. Sorry, make sure that you select the RX or the TX. You can plot any one of them. Here we go. That's the plot. That's the eye diagram. From the eye diagram, you can ask for all eye measurements. The second results, as we said, it comes from the second solver. So we used the transient solver and we have the quick eye analysis solver. So that's what's going to give you a clean eye plots. The user, by the way, can plot 3 types of eye diagrams from using the verify eye. So the first one is the straightforward one from here, eye diagram, rectangular plot. Then I select the eye solver, select voltage, and here you have to specify which probe. So let's select one of them. This is our probe, and automatically you see it gets populated with the right unit interval. You click new report, and this is the first one. So in this one, you can add the information about the eye. You can also notice that it is a function of the interval time. This is very important because we will show another kind of eye plot as a function of unit interval, not as a function of time. In addition, you see here, it also plots the response from 0 to 160 nanosecond. So you can see lots of data here. All of these are gathered and put in this plot. They overlapped. So you can see the eye diagram. You can also add a mask. So if you double click on the graph, you go mask, and you can edit here the mask, and you can add a mask. You can also import a mask from a file. And once you have a mask, you can also export it and save it as for future use. You can also add upper lower limits. So you will have something, not just a mask in the middle, you can have also mask on top and mask at the bottom. So lots of features you can add to this plot. Now the second way to do an eye plot is to go here and you add stacked eye diagram plot. Same thing, you select quick eye solver, you have the probe, and you go ahead, you see this unit interval is populated with the right number. You go ahead and we have a new plot. You can add all eye measurements. Again, it's a function of the time interval. And the eye diagram, eye plots, eye measurements. So it's a function of the time. It's a function of time in nanoseconds. Also, all the information of the eye are plotted to the left of the eye diagram in much more organized way. Unfortunately, with this one, you cannot add a mask. So this kind of plots, you cannot add a mask. The third way to plot an eye diagram is to go to statistical eye report and you ask for statistical eye plot. And you go here, quick eye, same thing, a new report. Notice here that its plot, the first thing you would notice is that its plot as a function of a unit interval. So everything is normalized to 1. From 0 to 1. That's the difference between this one and the other previous two plots. Here you can do the same thing. You can add all eye measurements. They are in unit. Notice here also that everything is normalized. So the eye width is 0.9915. You can also add a mask. If I double click here, you can add a mask. You can add a histogram. You can add a legend. So it has all the features of the first kind of plot that we saw before. So these are the 3 different types that you can use to plot eye diagrams and study and do analysis and do investigations on the accuracy and the signal integrity of your traces. In addition to the quick eye solver, you also have the verify eye. So you go here and you select verify eye, which is going to do a statistical analysis. is going to generate what we call a bathtub analysis. I can click here and I can run this one. So now we can look at the results after we finish the analysis. We go result, create standard report. It's not looking at the eye. You are now looking at a standard report, rectangular plot. You specify that you want to see the results from the verify eye analysis, and bingo, you have the bathtub. Again, you specify the probe and you say go. So we get our bathtub results. Now in here you can add a marker, what we call a y-axis, a y marker, and you can move this. This will help you to tell what is the width of your eye at a specific bit error rate. This is the bit error rate in logarithmic. So 1.1 and 0.001. So now you can tell what is the width of your eye at a specific bit error rate. So if I double click on this marker and I go to the marker, then you can specify the value of the bit error rate. For example, if I want 1e minus 6, so it's okay. It will move to 1e minus 6. That's the bit error rate I'm looking for. And this will tell me that the eye width for that bit error rate is almost 1, almost perfect, 0.999. And that's how we use this kind of plots to verify the bit error rate of our signal, of our trace. Going back to Signal Integrity Wizard, this time we would like to add IBIS models. So we go here and we say, for example, for the driver, we would like for the receiver, let's start with the receiver, much easier. We're going to select, let me select this one first. The receiver, so we have a receiver and we have an IBIS model. Let's select MT4, this one, right? Selector if you want, and we'll select DQ, and we'll select, and we'll select 3200. We say update, it's going to be updated. Now we go to the driver and we select, same thing, we select all the rows. Now we go here and we select vertex 5. And here we're going to select HSTL3, update. And we are ready to go. So proceed. We go here and we say with IBIS. And these are the results. So notice here that now we have IBIS models in our schematic. So on the receiver side, instead of having a termination and an eye probe, now we have an IBIS receiver and the eye probe. Of course, you need the eye probe if you want to look at the eye diagram, unless you want to use the transient, as we said before. On the transmitter side, also we have an IBIS model instead of having the eye probe connected directly. But this eye source is connected to this IBIS model, as we're going to see now. Now, if we double click on the definition of the IBIS models, so the first one is the name of the IBIS model, vertex5.ibs. The second one is the model and the type. Remember, we were talking about the type, whether it's min, max, which corner, which in SIwave it was called corner. This is where you specify it. And this is the power. So you specify it as internal because it's coming from within the IBIS model. The buffer is input output. Now the buffer could be input, could be output, and could be input and output. If it's input, then you know that this is a receiver. And if it's output, you know immediately that it's a driver. But when it's input and output, it means it can be both. And once it has this option, then you need to come here where it says buffer mode, and you need to specify that in this case, you want it to be an output buffer, which means you want it to be a driver. Polarity, that's the polarity of the signal, whether you want it to be inverting or non-inverting. Pin name, that's the pin name from the system. And the component name, again, that's coming from maybe the IBIS model name. Package selector, so we have pin or package. Again, these options exist in the IBIS model. So there will be sections in the IBIS model where you can specify whether this is a package or it's a pin definition. So there are two different sections, and you can select this or this. Probe die site, this is if you wanted to have a probe. If you specify this, then you have to enter the probe here. Now, the most important thing you need to notice is the logic in. So the logic in is the I source. So it's coming from the external source that you see here. So you need to link them together. If you go ahead and you say, no, I don't want it to come, which means the bits, the PRBS. With this setup, if you go to bits here, it's empty. There's nothing. There's no need for you to define anything because everything is defined from the I source and from the IBIS model. But if you select to have it to be internal, then automatically that section will be opened for you. And now you have to specify the rising time, the fall time, what kind of signal, the bits per second, how much bits per second PBS. You need to specify the PBS. And all the other information that's supposed to exist in the IBIS model, you need to specify them manually now. So we do cancel, go back. Again, we come back here, back to our setup where we are still relying on the I source. All these information, there's still more if you ask for. And here you have more control over your IBIS model by controlling the pull up and the pull down and the out of in option. And you can control the power pin, the ground, and all these options in the IBIS model. This is practically what you're doing. You're modifying or interfering, overriding the information that exists in the IBIS model. For whatever reason, the user needs to do something like this, then it's available to him. Most of the time, you don't need to do that. You just stick to the setup, the original setup. And you click OK. So we do cancel because we don't want to change the setup. So everything is ready for us. Now we can look at exactly the eye diagram. You see it's totally damaged, modified because of the contribution of the IBIS model at the input and the output. And also you can look at the waveform at the input, at the output, and the waveform at the driver. Of course, the one at the driver is affected by the buffer itself in the IBIS model. There will be a special session about IBIS models where we're going to explain more about this IBIS models and their setup. And we'll talk more about so many options and so many things that a user can do with IBIS models in the circuit. Thank you for listening.